So have you ever looked at a sequence of numbers and just wondered what ties them together behind the scenes? Take the numbers 24, 36, and 60. Now, on the surface, they're just three even numbers, right? Maybe you recognize them from the face of a clock or some measurements in geometry. But if we dig a little deeper, they actually share a hidden numerical DNA that connects them in some pretty fascinating ways. Today, we're going on an investigative quest to find that exact DNA, and more importantly, we're going to learn exactly how to extract it. Welcome to This Explainer. I am absolutely thrilled to guide you through this today because we are going to use a foolproof visual tool to demystify what can honestly feel like really complex math problems. We're going to completely crack the code on finding the highest common factor, the HCF, and the lowest common multiple, the LCM. And we're going to do the whole shebang using the highly visual, incredibly satisfying branching method. If you've ever found yourself totally lost in a sea of numbers trying to find common multiples, well, you are definitely in the right place. Here is our roadmap for today. First, breaking down the numbers. Second, comparing the prime factors. Third, finding the HCF. Fourth, finding the LCM. And finally, number 5, the golden rules. Let's jump right in. Section 1, breaking down the numbers. Extracting the DNA. Okay, so to really understand how numbers relate to each other, we first need to find their fundamental prime building blocks. Just like everything in biology is made up of basic building blocks, every number is built out of prime numbers. A prime number, just as a quick reminder, is a number that can only be divided by 1 and itself. We're talking about numbers like 2, 3, and 5. So let's extract the DNA of 24 using a visual factor tree to branch it down. What two numbers multiply to make 24? Well, 6 and 4 do the trick. So we draw 2 branches down to 6 and 4. Now, neither 6 nor 4 are prime numbers, so we just keep branching. The 6 splits into 2 and 3. The 4 splits into 2 and 2. And suddenly, we can't go any further. 2 and 3 are prime. We have literally hit bedrock. Now we just gather them all up. We have 3 2s and 1 3. So mathematically, we write the prime factorization of 24 as 2 cubed times 3. See how clean that is? Let's move on and see how this builds with our next number, 36. We're going to use the exact same branching process, but let's speed up the pacing just a bit. 36 branches down beautifully into 6 times 6. Both of those 6s branch down into 2 and 3. So, reading across the bottom of our tree, our raw DNA is 2, 3, 2, and 3. When we group the matching numbers together just to keep things nice and tidy, we get 2 2s and 2 3s. Therefore, the prime factorization of 36 is elegantly written as 2 squared times 3 squared. All right, let's keep that momentum going with our final number, 60. By now, you can really start to see the visual consistency of this tool. 60 branches into 12 and 5. Now, 5 is already a prime number, so that branch is completely done. It just hangs out there waiting for us. But the 12, that keeps branching into 3 and 4. The 3 is prime, so it stops. The 4 branches one last time into 2 and 2. So gathering all our bottom prime endpoints, the 5, the 3, and the 2 2s, we assemble our final equation. 60 equals 2 squared times 3 times 5. And there we have it. We've successfully extracted the DNA from all 3 numbers. Section 2. Comparing the prime factors, the complete picture. Now, finding the genetic code of a number is fun, but the real power comes when we organize this data to see exactly how these numbers interact with each other. By lining up our extracted prime DNA in a unified table, we create a seriously satisfying moment of organization. Over on the left, we have our original numbers, 24, 36, and 60. On the right, their prime factorizations are neatly stacked. 24 is 2 cubed times 3. 36 is 2 squared times 3 squared. 60 is 2 squared times 3 times 5. Letting you see the genetic makeup side by side like this takes all the mental juggling right out of the equation. We don't have to keep numbers floating around in our heads. The visual organization is doing all the heavy lifting for us. Section 3, finding the HCF, the shared traits. The highest common factor is the largest single number that divides perfectly into our group without leaving any remainders whatsoever. We are strictly looking for what these numbers share in common. And to do this without any guesswork, we use a highly logical 4-step formula. Honestly, this is a simple mental checklist you can use every single time. Step 1. Prime factorize each number. Check, we did that with our visual branches. Step 2. Compare the factorizations. Check, we just built our summary table. Step 3, and this is the magic key. Choose the common prime factors using the smallest powers. And finally, step 4. Multiply them together. So let's see step 3 in action. Right, so the absolutely crucial point is applying that third step. We look at our 3' factorizations. Which space numbers show up in every single row? Well, the number 2 is in all of them, the number 3 is in all of them. The number 5, however, is only in the 60 row, so it gets completely ignored for the HCF. Now, we take those shared bases, the 2 and the 3, and we look for their smallest exponent, the smallest power. For the 2's, we have a 2 cubed and 2 squares. The smallest power is 2 squared. For the 3's, we have 3 squared, and 3. The smallest power is just 3 to the power of 1, or simply 3. So we've carefully selected 2 squared and 3. And for step 4, the big reveal, we multiply our selections. What is 2 squared? It's 4. And 4 times 3 equals 12. There it is! 12 is the highest common factor. It is just incredibly satisfying to reveal that final calculation and realize you didn't have to guess or check a dozen different multiplication tables to find it. This method really proves just how elegant math can be when you break it down visually.
Section 4, Finding the LCM, the complete collection.
Now, let's pivot and look at the other side of the coin. The lowest common multiple is the smallest container that can perfectly hold multiples of 24, 36, and 60. We use the exact same factorizations we already built, but the rule flips. Instead of looking for what they strictly share, we want to gather up everything. We must identify every single prime factor present across all the numbers, and this time we take the highest power of each. Let's look back at our DNA pool. We have 2's, 3's, and a 5. What is the absolute highest power of 2 that appears anywhere? It's 2 cubed, from the number 24. What is the highest power of 3? It's 3 squared, from the number 36. And what is the highest power of 5? Well, there's only one, so it's just 5. We take our collection, 2 cubed, 3 squared, and 5, and we walk through the grand finale of our calculation. 2 cubed is 8, 3 squared is 9, and the 5 stays a 5. So we are multiplying 8 times 9 times 5. 8 times 9 gives us 72, and 72 times 5 lands us squarely on our final multiple of 360. Just think about how long that would have taken to figure out by manually listing out multiples of 24, 36, and 60 on a piece of scratch paper. The prime factorization method gets us straight to 360 with clean, undeniable logic. Section 5. The golden rules. Never get confused again. You know, the most common pitfall when learning this is simply mixing up the rules at the very last step. Let's lock in the correct logic right now so you never second-guess yourself again. Think of the HCF as a strict, exclusive club. It only allows factors that everyone has in common, and it only lets in the smallest power of those factors. It's super restrictive. On the other hand, think of the LCM as a giant, inclusive party. It invites every single prime factor that shows up anywhere, and it always demands the highest power of each. HCF, smallest power, only common. LCM, highest power, every prime. Keeping this little comparison in your mind will make the distinction absolutely unforgettable. We've seen how effectively this branching method cracks the code for 24, 36, and 60. By stripping numbers down to their prime DNA, organizing them, and applying 2 very distinct logical rules, what once seemed complicated becomes incredibly straightforward. So I'll leave you with this question to ponder. How can you apply this visual branching method to crack the DNA of even larger, more complex numbers? The true beauty of this tool is that it scales up endlessly. I hope you are eager to test out this foolproof method on your next big math challenge. Thanks so much for joining me on this explainer, and keep looking for the hidden structure in the numbers all around you.